and welcome back to your last and final part of your multimeter tutorial. Okay, part 5. In this we're going to be going through more tests on two multimeters. Okay, and we're going to be measuring, well, showing you how to measure component values. Okay, how to measure them, and why you can only measure them out of circuit. Okay, it's impossible to measure a component value in circuit, especially when it's powered. So a circuit's powered is a potential to damage a multimeter. Okay, very important you measure them out of circuit, and especially if they are in circuit and you want to measure in circuit, make sure that the power is off and that it's disconnected from your supply. Okay, even though the supply is off, it has to be disconnected. So let's make a start. Okay, to measure, let's start off on the resistances. Okay, resistors, measuring resistors on the fluke. What you need to do, first of all, pay attention to your sockets down the bottom. Now, which one is for measuring resistance? Have a look. I'm pretty sure that you can work it out. It's the ohms one. Okay, so that's what we use. As you can see, we've got some resistors down here on the board. I've got two resistors in parallel in series with another resistor. Okay, and to measure a resistance, doesn't matter which way around you put these probes. Okay, you can measure resistance. Okay, so just place them across the leads of your resistor, and there we have it. On the multimeter we have a resistance reading. Now that is a brown, black, orange, gold resistor. It is a 10K 1%, 5%, not 1%, 10K 5% tolerance resistor. And on our meter you can see 9.98 kiloohms. There you have it. That is our resistance measurement, and that's all that you need to really understand. Doesn't matter which way around that you connect these, don't have to worry about polarity. Okay, there we have it. Okay, now a couple of things that you need to understand. Okay, measuring in circuit is all very well and good, providing nothing is in parallel with your component. Ideally, the component has to be out of circuit if you want to measure. Okay, the reason for that is because you'll have another impedance with your resistor, two resistances in parallel. If you measure across them, like we are with the there we go, you've got a 1K in parallel with a, what's this, a 15K resistor. Okay, we're actually measuring 0.9 kiloohms. Okay, so it's definitely not 1 kiloohm. It's less than a kiloohm, and we measure so this 15K one. You can see that it is in actual fact the same as our previous reading. Okay, so 15K isn't a 15K according to this meter. That's because we're measuring it in circuit, and there's other components in parallel to it. So ideally, you have to unplug your component and measure across the two wires, and there we go. We've almost got a 15K resistor. It's 5% tolerance. That's a little bit out, but that's acceptable. And there we have it. So, good tip, good practice. Whenever you want to measure components, measure them out of circuit. If you have to measure them in circuit, make sure they're not in parallel with any other component. And normally when you're measuring in circuit, there's going to be other things in parallel with it, regardless of what's going on. For example, I have here my power supply. I will switch it off. I will plug this in to our circuit. Now we're going to measure this 10K again. What would you expect it to be? My power supply is off. Okay, and I read 2.3 kiloohms. Even though my power supply is off, it's still giving me the wrong value. It's definitely not a 10K. when my power supply is on, it's actually overload. Now why would that be? Now then, the reason for that, first of all, the component is now in circuit with our power supply, so you've got an impedance here on these two terminals, and that's actually in parallel with our circuit. We're applying a potential across here. When it's off, it's floating, but it's still got something there, even though it's off, and it's still going to give us a false reading when we try and read things in circuit. And it gets even worse when we actually switch things on, because we're applying a voltage across our resistor. And like I said before, resistor multimeters measure everything in terms of voltages. So if you're plugging a voltage, it's being dropped across this resistor. No matter what happens, you're going to get the wrong reading, because this is going to supply a voltage in order to measure a resistor, and this is supplying a voltage in order to power the circuit. You've got voltages everywhere, and you're not going to be able to measure anything, which is why you can never measure anything in circuit, especially when it's on. If your circuit is powered up, be especially careful of that, because you can in actual fact damage your multimeter. Okay, so what you're doing is you're applying power, you've got a power drop, you've got a voltage drop across this resistor, and you're applying this voltage drop to your meter, but your meter's already applying a voltage. Okay, so you're setting up a voltage here, essentially a current, and you're setting up a current here. They're flowing back in on each other, and eventually this thing is probably going to give up at some point, because you're starting to dump power internally to this, which is a pretty bad thing to do. Now then, before I move on to capacitors, I'll show you this little problem that measuring resistances has, and that's measuring a very low resistances. Now I've got a 1 ohm resistor here. Okay, it's a high precision resistor, 1 ohm, 1 watt, 0.4% tolerance resistor. Okay, and what happens when I connect this on the voltage range? Well, as you can see, it says it's 1.2 ohms. Now, if I told you that this was a point of a percent, 1 ohm, 0.4%, that's a pretty high error. Okay, that's actually 0.1. Okay, it's nowhere near 0.1%. So what's going on? Well, what we're actually measuring here is not only the resistances of your resistance, but also measuring these, your probe resistances as well. Okay, your multimeter is calibrated to measure your resistance at the terminals. It's not calibrated to measure the resistance at the end of your wire. So when we join these two probes together, you can actually see there is a 0.2 ohm. So when it was originally 1.2, it's actually almost 1 ohm, compared to 0.1, 0.2. It's actually fluctuating a bit. Okay, on your cable. So be very careful. If you have to take very low readings, you never know, one day you might want to measure, I don't know, the resistance of a coil, or the resistance of your inductors, I don't know, anything like cable lengths and so on. You know, how much resistance do you have per meter length of cable? Okay, measuring it on a multimeter, yep, you can do that, but you have to be very careful, so you don't measure very low resistances too well, because you do have to take into consideration the resistance of your probes. Now you can do what I've done here, join your probes together, find out what the resistance is, then subtract that reading from all of your resistor measurements. That's one way around it. Okay, so this is in actual fact 1 ohm, not 1.1 as it says, because the cable resistances. That is one way of doing it in order to overcome that error. But there are other methods of doing it, and you can do something called a 4-wire resistance measurement. Okay, 4-wire, because opposed to 2 you use 4 wires, and what you're doing is you're applying a voltage to your resistor, and you're actually, in actual fact, you're going to measure the voltage drop across the resistor and the current through the resistor. So you actually use a voltmeter and a current meter both together, and you can use Ohm's law, and that gives you your resistance. That's how you do it for using 2 multimeters, okay, and a source. But you can get multimeters with 4-wire measure multimeters. I do have one of those buried somewhere, not so sure where it is, but it is somewhere, and they're used for very low, high precision measurements. Okay, so there are ways around it. There's the tried and tested, touch them together, subtract the error method. Okay, that's one way of doing it, but you still get more error than you would using the 4-wire method. So that's your resistance measurements. What we're going to head to next is next one down, continuity. Same socket. Okay, continuity is all about testing point-to-point connections, making sure that you've got connections. You know, making sure that, I don't know, for example, the earth is connected to the outer chassis, which is connected back to the plug socket, and so on. And we can do that right now. So if we plug this one into the earth terminal of our power supply and we touch the chassis, you can hear we're getting a nice beeping sound. There is a direct connection, okay, between the earth and the chassis, and so on. Okay, so that's one example where you could use continuity. The other, more useful, practical sense, okay, in your building your circuits, you want to find out whether you've got a connection. If you think there's a break in your circuit somewhere, your circuit isn't working, I don't know, for some reason, it looks like that you've got open circuit, you can use a continuity check to check between the various points. So you can say, right, from my negative terminal here, it's not connected to a power supply, so plugging the multimeter into one, I can measure along the line to say, right, well, that point is definitely connected to there. My positive side, it's connected to the bottom of the terminal. Is it connected to the breadboard? Yes. Is it on the resistor? Yes. So on and so forth. You can trace routes of very low impedance, so a point-to-point test. So you're testing from point here to this point here, your component leg, to make sure that you've got connections. Very useful in fault finding. Okay. Get used to using those. Make sure things are all connected up correctly. Whatever you do, just like any other measurements, like the resistance measurements, you can't do it when the power's on. Okay, make sure that your power supply is off, or at least that it's disconnected, or at least it's off. Okay, otherwise you will be potentially damaging your meter. It's actually applying a voltage and measuring the connection. Okay, and that's that one. Moving on, next one down, diodes. Diode test is very useful. It tells you whether you've got a working diode, a blown diode, whether it's forward bias, whether it's reverse bias, and what its turn-on voltages are. So let's take a diode. We've got a diode down here. Okay, simply connect it to between your probes, same sockets again. It's diode test down there. That way around. Okay, we've got overload. That means that it is reverse biased. Okay, at the moment. Turn it the other way around. We're getting a reading of 0.3 volts. Forward bias, its terminal voltage is 0.3 volts, and that's about right, because this is a germanium diode. Okay, it's got a very low turn-on voltage, as opposed to silicon, which is about 0.7 volts, 0.6, 0.7. Germanium's about 0.3. Okay, very rare to get hold of germanium diodes now. They're dying out. Okay, silicon is taking over. So that's a diode. And just highlight the fact that it doesn't always give you 0.3, it does in actual fact give you the terminal voltage. Let's do it for an LED. Okay, that way around. Overload, it's the wrong way around. Connect the anode and cathode around the right way, and lo and behold, look, even the LED lights up, and it has a terminal voltage of about 1.8, 1.779, 1.8 volts. Okay, so you know exactly what voltage you need to turn it on with, and that if you have it connected around in your probes this particular way, you know that it in this way around, you know what the anode is, you know what the cathode is, you know which way around to connect it to bias it correctly. So very useful diode measurers for testing your diodes. Okay, very quick and very dirty way of doing it. On the fluke, okay, as opposed to your Beckman multimeter here, okay, the fluke has a capacitor reading. Okay, you can measure capacitances. Can't measure all capacitances. There are very low value capacitances it can't measure, and there's very high values it can't measure. Just like frequencies, it's got a set range because it uses the internal clock in order to generate a wave, okay, that can be used to calculate the reactance, its impedance of a capacitor. It will display the resistance on the screen. So for example, I've got here a ceramic multi-layer capacitor. I won't bother looking at what value it is. Let's connect this up. It's non-polarized, so I can connect it any way around I like. Oops, what haven't I done? It's in yellow. Okay, make sure that you press the yellow button. It sends it into the other mode, measuring mode for capacitances. So let's connect that up. And we've got a 418 nanofarad capacitor, and if I look at this capacitor, it's written 474. Okay, this is in actual fact 470 nanofarads. Okay, 0.47 micros, but it does have tolerance just like all other components, and it's closer to 480 nanofarads. And that's a ceramic. Same can be said for electrolytics. Now, electrolytics are polarized. You can see the markings there, negative markings, so connect the negative to your common, connect it around the right way, and lo and behold, this is written on here. It is a 4.7 microfarad, and it says it's a 4.47 microfarad, so it's very close. Remember, tolerances, electrolytics can have a very high tolerance on them. Okay, higher the capacitor value, higher the tolerance, unless you're willing to pay out a lot of money for high precision. With precision comes expense, and that's measuring capacitances. Okay, just like with the resistors, you can only measure these devices out of circuit. Measuring them in circuit with a supply though, okay, you've got a voltage dropped across them already, you can damage a meter. Can't stress that more. And you definitely can't measure them when they're in parallel with anything else. So even if your power supply is off and it's still connected, you're not going to measure anything particularly well. Okay, so there you have it. That's the fluke multimeter done. Okay, moving on to this one, the Beckman. Does everything the same as the fluke. The only difference is on this one it's not auto ranging, so you've got to set your range for measuring your resistances. Diodes works exactly the same way. Okay, you still plug it into your socket here. The only real difference is instead of measuring capacitance, it measures transistor HFE, okay, transistor beta. So let's do that. How do you do that? Turn it round to HFE. And do I have a transistor handy anywhere? Yes, I do. I have a transistor on my desk. Okay, so we'll plug this in. I think it goes that way up. Emitter-based collector. Plug it into the sockets. Lo and behold, it gives you its transistor gain, its HFE, or its beta if you want to call it its beta. I prefer HFE. There you go. Just match up the emitter-based collector. This is a very low voltage measurement on the Beckman, so if you do connect it around the wrong way, Okay, you do it upside down, plug it into the wrong sockets. You're not actually going to damage the transistor. Okay, still 124. There we go. That's how you measure gain of a transistor. It's an NPN. Exactly the same for PNP. You just leave it on a HFE. You plug it into the other socket, and hey presto, you got the HFE for a PNP transistor. Okay, there's not rocket science in the least. And measuring components, very straightforward. Rule of thumb: don't connect them in a circuit. One other thing that I'd like to mention: always make sure that your capacitors are fully discharged. Okay, whenever well, it don't have to be fully discharged, but you want to discharge them down so there's quite a small charge in your capacitors. Okay, if you've got a lot of charge stored up in your capacitors, it can damage your meter. Okay, so just remember that. Okay, capacitors like to store a charge. Bigger the capacitance, bigger the charge. Okay, these don't have any internal resistances, so if you do use them in with very low, a series of very low resistances, you know, you can end up dumping all the power from these straight into whatever you're using. So if you do, when you do discharge them, the larger ones, be very, very careful. Discharge them safely because they will spark or arc. Don't you hurting yourselves. And when you do attach the big chunky ones, like what you use in power supplies, or maybe to hold charges for CRT screens, things like that, be bloody careful with them. Okay, they're dangerous as hell. I've seen people get electrocuted and having really nasty burns because they've haven't discharged the capacitors properly, and they've touched the wires, the terminals, and they've got a bit of a shock. The ones that I've got here in the lab, you don't have to worry about that too much, except for the ones which are up in the millifarads, but they will still give you a shock if you're not careful, especially if you've got damp fingers. So just a little bit of a warning there. And if it is a particularly cheap meter and it has got a capacitance measure, pay particular attention to the range. You don't want to whack in something with a big charge and blow the multimeter. It does happen. Okay, a few hundred joules can be easily stored into one of these, into one of the larger ones. A few hundred joules dumped all in one go, that's a big bang. Okay, and that's it for your multimeter session. All done. New piece of kit on the next tutorial, whatever that might be.